All right, the next topic that we're going to talk about is verifying trig identities. Okay, so first of all, an identity, remember, is something that is true. Okay, so an identity involves an equation that is true, and we want to kind of show why it is true. Okay? Now, one important thing that I want to talk about is the difference between verifying and solving. Okay, these are two very different things. Okay, so to start with, I just want to kind of talk about an example of what I mean. Okay, so solving, we're going to start with solving. We've kind of lived in the solving world for a really long time. So for example, I could solve an equation like x squared equals 4. Solving this equation would involve something like square rooting both sides. When I'm solving, I have to do the same thing to both sides of my equation, and then saying, okay, the square root of x squared is x. The square root of 4 is positive or negative 2. So this is my solution. X is equal to positive negative 2. That is solving. That's a solution. Verifying looks very different. Verifying might ask, verify, I cannot spell verify, I'm sorry, verify that x equals negative 2 is a solution of x squared equals 4. This is a verify question. To verify this, we simply take negative 2 and we plug it in and show that negative 2 squared is in fact 4. Okay, this is the kind of verifying we might do in algebra, verifying versus solving. Okay, in trig, when we're verifying, we're going to take something like a Pythagorean identity. Okay, so one of our most bestest is what I really wanted to say, which is not good English. One Pythagorean theorem says Pythagorean identity says that sine squared of x plus cosine squared of x is equal to 1. Okay? If we are asked to verify this, notice that this is not solving. We're not saying solve this for x. That's something completely different. In fact, that would be really, really challenging to solve this for x. Okay? Verifying just means show why this is true. Okay? So we're going to look at several techniques for how we verify things. But one thing we can do here is what we did way back in the day. Is I can say, okay, if I want to verify that this is true, I maybe want to rewrite my sine squared of x using kind of my opposite over hypotenuse relationships, or thinking of sine as y over r, which means sine squared is y over r squared. Similarly, cosine squared will be x over r squared, and we're trying to show that that's equal to 1. That's what a verify is doing. It's trying to show that both sides of the equation are equal to 1. Now, or are equal to the same thing, in this case equal to 1. Now, we're right now using one of the techniques of verifying, and that is start with the more complicated side. Sine squared plus cosine squared is much more complicated than 1. Try and make it simpler, okay? So that's kind of what we're doing. So what could we do from here? Well, y over r squared is the same thing as y squared over r squared. X over r squared is the same thing as x squared over r squared. Okay, and then I can put those together because this is now a common denominator. So over r squared, I'll have y squared plus x squared. Okay, but remember this is coming from the unit circle. And it's not coming from the unit circle. This is coming from our right triangle trig. And in our right triangle trig, right, we have x, we have y, and we have r. And by the Pythagorean theorem, we know that x squared plus y squared equals r squared. So that means y squared plus x squared, which is the same thing as x squared plus y squared, equals r squared. So this left-hand side becomes r squared over r squared, but r squared over r squared is 1. So we've now shown that the left-hand side is equal to 1, and the right-hand side was equal to 1. So we've verified or shown that this equation is true. Notice that that does not mean I solved anything. I didn't solve this thing for x. I just showed that it is a true statement. Okay? So that's kind of the idea behind verify. We're going to be given an equation that we know is true if we're asked to verify it, and we are going to have to use what we know about trig to try and show why it's true. Okay? So your textbook actually gives a pretty handy kind of shortcut guide to how we might do some verifying. So I'm just going to pull that up and we're going to talk through it a little bit. Okay, so let me share. Okay, so when I share this screen, here are our hints for verifying identities. So the first hint says we need to know those fundamental identities. So we need to know our reciprocal identities, our quotient identities. We need to know our even and odd functions and what that means. And we need to know our Pythagorean identities. Okay, we're going to use those things a lot in our verifies. Okay? So number 2 is exactly what we tried to do in this last example. And it says try to rewrite the more complicated side of the equation so that it reduces down to the simpler side. That's what we did when we did sine squared plus cosine squared equals 1. We took the more complicated side and rewrote it or broke it down. Okay? Number 3 says it's sometimes helpful to express all trigonometric functions in the equation in terms of sines and cosines. Well, in our last video, our last example, we actually did that. We broke things down into sines and cosines and then reduced. That can be really useful for verifies as well. If we can rewrite everything in terms of sines and cosines, cancel things out and show that the left and the right are equal, we're good to go. Okay? All right, so usually any factoring or indicated operation should be performed. So what does that mean? So if we have something that looks like their example, sine squared plus 2 sine plus 1, we can factor. So what does that mean? That means algebra not going away. We're still going to have to use algebraic techniques like factoring or distribution as we're doing our verifies. Okay. Next, it says when selecting substitutions, keep in mind that the side that is not changing, because it represents the goal. Okay. So sometimes we're tempted to change everything on both sides, right? To say, okay, this looks like a Pythagorean identity and this looks like a Pythagorean identity, so let's change both. It's often more helpful to start with one side and work with one side until you really can't work with it anymore. And then if you have to, look at the other side. Sometimes working both sides of a verify or both sides of the equation can be counterproductive because you end up chasing your tail or going in circles. So start with one side, usually the more complicated side, and try to simplify that first before you go on both sides. Okay? Number 6, if an expression contains 1 plus sine of x, multiplying both numerator and denominator by 1 minus sine of x would give 1 minus sine of x, sine squared, which could be replaced with cosine of x. Similar procedures apply for 1 minus sine, 1 plus cosine, and 1 minus cosine. So this is just saying we can do some weird kind of algebraic stuff to get us to a place of a Pythagorean identity. Now, while that is true, I will also say that one's pretty tricky and it's one that we're not going to see too often because it's a pretty specific case. Okay? All right. So these 6 hints are going to be really, really helpful. In the next couple of videos, we're going to start going through different verifies so that you can get some practice. Here's the thing with verifies. You either love them or you hate them, okay? I think they're kind of fun because they're a puzzle, right? We're trying to show what is going on with two sides of the equation. We're trying to make them look the same. It's a big, giant puzzle. You're trying to find the right substitution or the right replacement. I think they're really fun. Some people may not share that opinion, and I get it. The other thing about verifies is the more you do them, the better you get at them, like most things. But this is particularly true, I feel like, for verifies, because you start to see kind of common techniques that you can use to simplify one or the other side of the equations, and that just gets easier as we go on. All right, so that gives us a place to start. Now let's work some examples.